The topics that plan to cover are the technical specifications of the supercomputer, the Cheyenne supercomputer, and also the modifications to the Glade file systems, the Cheyenne computing environment, how to access software on Cheyenne. That includes compilers, it includes MPI libraries, and different ways to get parallelism in your codes, how to submit batch jobs using the PBS scheduler, data storage, where you can put things after you've run your simulations, and then, again, remotely we can do a Q&A, though feel free to send those questions at any time. So Cheyenne is an evolutionary increase from Yellowstone, meaning that both systems have a lot of commonalities. It's just that Cheyenne is a more powerful and slightly more advanced version of Yellowstone. And that should make the transition for you when you're moving codes and moving your workflows pretty easy. So Yellowstone was a 1.5 petaflops, or is a 1.5 petaflops machine. Cheyenne is 5.34, so you can do the math. It's a pretty good increase in compute power. The number of nodes is actually a little bit less, but the nodes themselves have more cores on them, and cores are what you request when you do your job scripts. So there are about twice as many cores, and the cores themselves, or the CPUs themselves, are more powerful. So Yellowstone has the Sandy Bridge variant of the Intel processor, and Cheyenne has the newer Broadwell variant. There is 145 terabytes of total memory on Yellowstone, 32 gigabytes per node. Now on Cheyenne, we have the majority of the nodes, 3,164, with 64 gigabytes memory, so double. And then we have 864 nodes, which are considered high memory nodes with 128 gigabytes. Now it's important to note that these memory numbers are not, for both machines, are not what's strictly available to jobs. There are certain tasks that are operating, like the file system. The Glade file system actually uses some memory while your jobs are running. And there's some other processes that are using memory as well, including the operating system. So the usable memory limits are a bit lower than those numbers, but it's important to note that you'll have quite a bit more to work with for your jobs on Cheyenne. And then the interconnects, the communication fabric between the nodes, is also about double the speed on Cheyenne. So when your codes have to pass messages between the nodes, it can do so at a faster rate on the Cheyenne hardware. So all of this summed up basically means that about 1 Yellowstone core hour should be equivalent to about 0.82 Cheyenne core hours. So when you're thinking about your accounting and how many core hours you need to accomplish your project's goals, that's a pretty good guideline to use. That's what we advise you use when taking care of that. So in addition to the compute hardware being an evolution, we're also modifying or bringing in advances on the file systems, the Glade file systems. So first, the first order, it's an expansion of the space, which is useful since we'll be generating more data with that more compute power. Now, the Glade file systems will continue to use IBM's GPFS spectrum scale technology. Spectrum scale is the newer name, but it's the same technology. The existing capacity, which is as of a few months ago, was 16 petabytes. Now, the new added capacity is 21 petabytes of space, so quite an increase. And that, of course, gives you a total capacity of 37 petabytes. And we have the potential for expansion to 58 petabytes total with future upgrades. And at this point, this is part of the plan. So in addition to there being more space, it's also faster storage. There's more than 2 times the transfer rates on the new Glade file spaces. So when you're using the scratch space on Cheyenne, you'll get quite a bit faster input-output speeds for writing files and reading files than you would on the Yellowstone scratch space. Now, one important thing to note, and if you haven't encountered this as an advanced user on Cheyenne, when you get on Cheyenne, you will encounter this, that home spaces are shared between the two systems. So if you have scripts or codes that have been configured for Yellowstone, and you will have equivalent scripts on Cheyenne, or for Cheyenne. They'll both be in the same place, and you have to be careful when you manage those two things that you have your files, for one, not writing over top of each other, and also that you are using the correct files. So that's one little management thing that you have to pay attention to. And the most immediate example of that is if you have configuration scripts which set up your environment when you log on to the systems, you need to make sure that the commands that you care about on Yellowstone, say LSF commands, are not being run on Cheyenne and vice versa. And I'll discuss that specific example a little bit towards the end of the talk. So that's a basic overview. Now getting into more of the day-to-day details. And a lot of these are very similar to what you do on Yellowstone right now if you're a Yellowstone user. So to log on to the systems, as before, you'll use your YubiKey authentication token along with your username to log into the machine. Of course, the main difference here is that you're logging into cheyenne.ucar.edu instead of yellowstone.ucar.edu. But otherwise, it's the same command. So that you'll then be on one of 6 login nodes. And these are identified as cheyenne1.ucar.edu, cheyenne2.ucar.edu, and so on. Your default shell is C shell, but others are available through SAM. So if you go to the SAM website, you can select between C shell or bash or K shell. Choose whatever you like. If you don't specify it, you'll default to C shell. Now, one difference on Cheyenne relative to Yellowstone is that on Yellowstone, we're running Red Hat Linux, Enterprise Linux. On Cheyenne, we're running SUSE Linux. So this provides mostly the same commands. There are very few differences visible to the user, but there might be some small differences that you run into from time to time. And if something seems different or confusing from the Red Hat environment, feel free to let us know at CISL Help, and we can work with you on that. But all of the typical Unix commands that you would expect are there. So just as on Yellowstone, it's important to note that the login nodes are a shared resource. So we expect you to use them pretty lightly. That means that your programs will compete with those of tens to hundreds of other users, depending on the population of users on the machine at any given time. And they'll compete for CPU cycles, and they'll also compete for the amount of available memory. As a result, it's not a good idea to run scripts that will run for a long time and use a lot of processing or use a lot of memory, because if they use too much, those scripts will be killed. They won't finish, and presumably you'll be disappointed. So limit your usage on the login nodes to reading and writing text or code, compiling programs, performing small data transfers. This could be to different HPC systems. It could be to HPSS, the tape archive, or it could just be between the Glade file spaces. Interacting with the job scheduler. So of course, if you want to submit a large model run, then you would do that from the login nodes. But again, programs that use excessive resources, even if it's a MATLAB script or something like that, on the login nodes will be terminated. So it's a good idea that if it's going to run for a long time, or it's going to read in a lot of data or write a lot of data, to run those in a batch job. So we build software for you to use in your computing environment. And we use environment modules to make those pretty straightforward to load and access. So we build programs and libraries that you can enable. Again, this includes things like compilers, parallel libraries. NetCDF is one we have many versions of. MKL, the Intel math library, which is a pretty optimized set of math routines. It's a good idea to take advantage of the MKL library, or I guess MKL, if you are using the Intel compilers. and you're doing intensive math operations. And then, of course, Python, MATLAB, R. So modules, what they do is they configure your computing environment so that you can find binaries, executables, you can find libraries and headers to compile with, and you can find man pages, manuals to reference. And you don't have to set up your environment every time that you want to access those things, which you would otherwise have to do if we didn't have the modules set up. They're also used to prevent conflicting software from being loaded. So if you have the Intel compiler in your environment, you don't want to load a version of netcdf that was built with the GNU compiler, because if that happens, then a lot of times you can get errors when you try to compile things that use netcdf. So this helps us help you avoid some of these tricky things with your computing environment. Now, of course, you don't need to use modules. You can set this all up manually, and you can do things that are kind of non-standard edge cases outside of the modules. But for most uses, they should help you simplify things greatly, and we do recommend that you use them. Also, if you're using our modules, then it makes it easier for us to help you debug problems when you submit a help ticket to us. Now, one difference is that, or one thing to note is that Yellowstone and Cheyenne each have their own module software tree. So when you do a module, when you do an available list of all the modules, they will be different on Yellowstone and Cheyenne. We've built we've built all these software packages over again for Cheyenne, and it's not a comprehensive list yet, of course. There's less software available right now on Cheyenne than there is on Yellowstone, simply because Yellowstone's been around for a bunch of years. But as we go through in time, you can request software that is missing that you need, and we'll get it on there. But they do have different trees, each machine, so don't expect to see the same things by default. There's also differences in the way that we're laying out the module trees, and that should hopefully make it easier to tell what's available, should add a little bit of choice, and just make the overall experience a little clearer. So to kind of diagram this out, on Yellowstone, what you would do is you might select a compiler. Let's say you select Intel, and then you'll get added into the module list all the software that was built with the Intel compiler. So it might be, you'll have the math library from Intel, you'll have a version of netcdf, a version of parallel netcdf, and you can select that. And if you switch to the GNU compiler, it will make the adjustments in terms of what you have loaded for netcdf, for example, as necessary. So that's one level of a module tree, and that's worked out pretty well. But we have noticed some situations where it doesn't work as well. One thing is it can be hard to tell if you load, say, version 440 of netcdf, what version of the Intel compiler that was built with. I know it was built with Intel, but was it built with Intel 16, Intel 12? There could be significant differences depending on which version of that compiler was used. So on Cheyenne, what we're doing is we are, instead of specifying that this software was just built with Intel, we're specifying that it was built with this specific version of Intel. So I'll see these different versions of the compilers listed, and if I load Intel 1603, then I'm going to get a subcategory of all the software that was built with Intel 1603. So here again, we would have the math library and netcdf. Now within that, you'll also have an option of selecting different MPI libraries. This is another change. On Yellowstone, the vast majority of users use the system MPI, which is from IBM. It's Poe, and that works. That's kind of a simple way to go about it. But if you have certain codes that don't work well with that system MPI, it can be tricky. So there are some that might work better with the Intel MPI, or some that might work well with another MPI library. So on Cheyenne, we're going to offer more choice. We do have a system MPI as well. This is the one provided by SGI. It's the SGI MPT library. Right now we have 2.15 is the version that's installed. And that's probably the one that you'll go with most of the time. But we'll also have the Intel MPI library. We have OpenMPI on there. And when you select one of these MPI libraries, then you get another subcategory of parallel software that was built with that compiler and that version of MPI. So this should, just by going through this module tree, make it pretty clear what dependencies you might have, because of course you don't want to have a version of PNetCDF loaded that uses OpenMPI, and then you're trying to run it with SGI MPI. That will generally not work out well. So this module tree helps us avoid potential issues like that. So in terms of commands for the modules, these, if you've used the modules on Yellowstone or on any other cluster that has environment modules, these should all be pretty familiar to you, or at least most of them. To add software, you do module add or load, and then to get rid of it, if you have it loaded, you can do remove or unload. Module avail or available shows all of the software that is installed on the system, and that's a nice way to get a list of what you can find. Module list will show all of the software that you currently have loaded in your environment, so it's a subset of this, of what's in module avail. Module purge will clear your environment of all loaded software, so if you want to start with nothing and then build your collection of software up, that's a good way to do that. Now, when you sign into the system, you get a default set of modules that we've configured. These are things that kind of cover probably the majority of the use cases on the system. It'd be the Intel compiler, as well as a version of NetCDF, some compiler wrappers, which make compiling a little bit easier, and also a environment module, NCAR ENV, which sets some settings for the models, it's like CESM. So that would be the default set, but you can create sets of modules and save them, and then restore them at different times, and that allows you to further customize your environment. Let's say you want to use the GNU compilers by default instead of the Intel compilers. You could do that with a saved module set. And finally, this command is probably not used as much, but I think it's a pretty useful one. If you do module show and then the name of the module, you'll see all of the commands that we've set up in that module that get run when you load the module. And that can help you see what we're doing when we configure your environment. And also, if you want to do a little customization, you can look at that and get a flavor for the commands that we run. So I'm going to go into the terminal right here. And if this is hard to see, please just let me know in the text and I can play around with it. I can certainly make the font bigger if need be. So right now I'm just on my local computer, but we can go and SSH into Cheyenne. Thanks, Christopher. I'm going to get my YubiKey out. Okay, so now I'm signed on to Cheyenne. You'll see I'm on the third login node. We have the daily B items, just as you're familiar with on Yellowstone, when you sign in. So right now, I'm in my home directory here. And if I do a present working directory, you'll see it's the same exact path, Glade, U, home, and then my username that you would see on Yellowstone. Again, this is a sign of having those shared file spaces, so it's something to keep in mind. Let's look at the module environment. So if I do a module list, you'll see that I have a version of the GNU compiler. I have those compiler wrappers, and then I have another piece of software which we use to install things on the system. But if I do, I'll just do this. This is a command I didn't specify, but it's a good one to know as well. If you do module reset, it will bring you back to the default set of modules. So now if I do a module list, I'll see the NCAR environment, the Intel 1603, NCAR compilers, the MPT parallel MPI library, and then NetCDF 4411. So this would be the current default. Now if I want to see what's available, I can do module avail and see here's a list of the compilers that are available. We have 3 different versions of GNU, 3 different versions of Intel, and you can see what's the default with the D there. We have this IDEP category, which is software that's built that should be independent of what compiler you have loaded, so I can use NC view, for example, with any compiler. So we only have one version of that. And then we have this category, which is software that was built specifically with Intel 1603. And you'll see that there's a bunch of options here. And then since I have MPT 2.15 loaded, I have this additional subcategory here of software like NetCDF MPI, PNetCDF, that was built with both that compiler and Intel 1603 and MPT 215. So that's how to read through this module tree. Now, again, I can do a module list to see what I have. And let's say I want to see how NetCDF is configuring my environment. So I can do a module show NetCDF, and I can specify the version if I want to. So this then shows the different commands that we run. So we add the binaries to the path. We add the manual pages to the man path. We set headers and libraries to variables that get used by the compiler wrappers. And then we set NetCDF, which is a variable that's used by Wharf, for example, to know where to find NetCDF when it does its compilation. Now you can also do module, I think it's module help, NetCDF, and that will give you just the help text describing what the module is. And also, this particular module shows what modules were used when it was built and when it was built. So that information can be useful to find more information about the software itself, and also can be useful information to give us when we're debugging problems that you might run into. Okay, so let's go back to here. So let's say you want to compile some software on Cheyenne. So we will support Intel, the GNU compiler collection, and PGI. PGI is not on there yet, but it will be. As on Yellowstone, we have compiler wrappers. That's that NCAR compilers module, which are loaded by default. And they should make including code and linking to libraries much easier. So you don't have to do the -I and -L commands to the compiler to specify headers and modules and libraries. That should just all be done behind the scenes, assuming that the software you're trying to link in and include is in a module, like NetCDF, for example. So, using that as an example, if I do this with the wrappers, all I have to do is run the compiler command. So for Fortran code, it'd be ifort. Here's my code itself, model.f90, and then I'm outputting it as an object model. And that would be the binary that I would then run. So if I have the NetCDF module loaded and the compiler wrappers, that's all I have to do. Now, if I don't have the wrappers loaded, then I would have to, I don't have to set this NetCDF variable. That's just a convenience variable, but I need to know where the path to the NetCDF build is. And then I'd have to include the headers. So NetCDF/include with a -I, specify my code, specify where the libraries are, so that would be in the lib folder. I would need to tell the compiler that I want to actually use that NetCDF library. This is the Fortran library, so NetCDF-F. And then again, I'm going to create a binary called model. So you see it's, a decent amount more complicated. It's certainly not something that isn't impossible by any means, but with the compiler wrappers, it's quite a bit easier. Now, again, I said this before, but let me emphasize, don't expect to run a parallel program using one MPI that you compiled with a different MPI. So if I compiled, let's say, Wharf with SGI MPT, and then I tried to run it with Intel MPI, I'm going to have problems. These need to be consistent. So if I build with a certain MPI, I need to use that MPI at runtime as well. Wasn't so much a thing to think about on Yellowstone, since the vast majority of folks just used the system MPI, but since we'll have more options here, it's something to keep in mind. Now, another thing to keep in mind while we have both Cheyenne and Yellowstone going is that where you compile your code should depend on where you intend to run it. So again, Cheyenne has newer Intel processors than Yellowstone and Caldera, and those two systems, in fact, have newer chips, newer processors than Geyser. As a result, they have different instructions to the CPUs, different ways to optimize, so that adds a complexity when you compile if you want to run across the systems. So if I want to have one version of my model, say CESM, and I want to run that on both Yellowstone and Cheyenne, it's important. What you should do is you should compile for the oldest system that you want to use. And that ensures that the results are consistent, and it ensures that you won't do any optimizations that prevent you from running on the older machine. So if I want to run on both the systems, I would compile on Yellowstone, and then I could run the same thing on Yellowstone and Cheyenne. However, if I compile on Cheyenne, there's no guarantee I can run that on Yellowstone. Now that's if you want to save yourself a little compile time, but probably the better idea is to build versions of your executables separately for each system. That'll give you the best overall performance. So if I build using optimizations on Yellowstone, and then I build another one using optimizations on Cheyenne, they'll both run to the the maximum potential, given all these other caveats on each system. But if you use different optimization levels, there are chances that you can have differences in your output, in your results. So it really depends on what your highest priority here is in terms of where you're going to build and how you're going to build. Okay. So the biggest difference probably in a day-to-day sense from Yellowstone to Cheyenne is the job scheduler. So on Yellowstone, it's LSF, and on Cheyenne, it will be PBS. So here's an example of a Yellowstone job script. You can see this one's in Bash, but this would be the same exact job script in C Shell. So we have our LSF directives at the top. These all start with the hash B sub. And then you'll have things like the job name, the project code, the queue, the wall time, the number of cores, how many cores I want per node, which we would do with a p-tile option on Yellowstone. And then you can specify the locations of your output log and your error log. In this case, I've set them both to be the same. And then finally, I'm going to run my executable. Here I'm running wharf, so mpi run.lsf, and then wharf. And that's assuming I'm in that directory already. Now on Cheyenne with PBS, it's pretty much the same, but the syntax is, of course, different. Here we have PBS directive statements. You have the job name, the project code. Here it's a -A, not a -P. That's something that can trip you up. Again, the queue, the wall time is set with this -L. That's a L, not an I, a lowercase L. -L wall time equals, and then you'll notice you'll have hours, minutes, seconds instead of just minutes, seconds. And then you'll have your resource request. So here we have 144 cores specified with a -N. What we do here instead is that we specify the number of nodes with the select. So here I'm asking for 4 nodes. Each of them have 36 CPUs, and I'm going to have 36 MPI processes, or MPI tasks on each. Now, so if you do the multiplication, you'll see that these numbers end up being the same. But that does bring up another hardware point here, that on Yellowstone, each node has 16 cores, if you're not using hyperthreading. And on Cheyenne, each has 36. So if you want a full node, if you want to actually utilize a full node, you would request 36, not 16. So here again, I'm having a log error file that's joined. Here I do it with a -join -j OE, and then I specify the log name. And then I run it down here with this mpi exec mpt omplace wharf.exe. So the mpi exec mpt is the same thing as mpi run.lsf. It's basically a script that takes my job settings and sends that to the MPI library. In this case, we're using SGI MPT. This omplace is a new little wrinkle on running jobs, and let's get a little further into that. So by default, when you run a job, your MPI tasks or your OpenMP threads will tend to migrate across available CPUs through execution, meaning that if I have a task that's MPI rank 0, that might go from the 0 core to the 1 core to the 4 core, moving around the CPU as the job runs. And the operating system handles this behind the scenes, and it does that to try to balance the load. That's what happens by default. But it's often advantageous to pin tasks to a particular CPU, meaning that those MPI processes or those OpenMP threads can't move around. They're locked to one place. And that can be useful if I want to exploit, say, how close my memory is to the actual CPU. And if you shrink the distance that data has to travel from memory to the CPU, you can sometimes get better performance. So it can be advantageous to pin tasks. It's pretty much never disadvantageous to do so. So that's what this omplace command does, is it basically says, I have this resource request here. Now set that up in an optimal way and make sure that my tasks, my MPI processes or my OpenMP threads or my P threads don't migrate around across the node. So here's an example. Let's say I wanted to have a hybrid job, and in this hybrid job I'm exploiting two different types of parallelism. I'm exploiting distributed memory parallelism with MPI, and I'm exploiting shared memory parallelism within the node using OpenMP. So here I'm asking for two nodes, which each have 36 CPUs or cores. I'm asking for two MPI processes and 18 OMP threads per MPI process. So again, if you do the math, 2 times 18 is 36. So what I'm asking for here is I'm asking for one MPI process per socket. Each node has 2 sockets. And if you've ever seen a picture of a CPU, like an Intel CPU, each one of those goes in a socket. So you basically have 2 physical CPUs that you can put into a socket within a node. Now, and then I'm going to have 18 threads, 1 in each socket. Or sorry, 18 in each socket. So omplace will basically take my resource statement here and make sure that all is set up in an optimal way. Because of course I don't want both of my MPI processes on the same socket and some amount of threads on a socket that's not what I want. You know, I want one MPI process on each socket and 18 OpenMP threads per MPI process. So omplace will make sure that that happens in a logical way, in the way I've set up. And omplace will also make sure that those threads and those MPI tasks don't move around, because I don't want them to. I want them to stay where they are because that's the best for the way I'm using my memory in my program. Now, it's almost never detrimental to pin tasks in this way, so that we advise you to use it for all of your parallel jobs, unless you have explicit reason not to. If you know that that will decrease your performance, we suggest that you do use it. So all of the examples that I have will show this omplace command. And we have a website on the CISL help pages that describes this in more detail and has some diagrams which probably make this a little bit clearer in terms of the layout of the nodes and how that can be beneficial. So again, just some examples of using different types of parallelism. If I want to use threads, either P threads, POSIX threads, or OpenMP threads to exploit some shared memory parallelism, here's an example of how to set up a job script to do that. Now, of course, my program needs to be compiled with the OpenMP library first off. But once I've done that, if I want to actually set this up to work in a job, I can do this PBS resource request. I'm requesting one node. I want to use 10 of the 36 CPUs, and I will have 10 OpenMP threads. And the way I can run that, making sure that I'm pinning the threads, is to do omplace -nt, say $OMP num threads. That's an environment variable. I could also just write the number 10, but if I use this variable, I don't have to update that if I change my number of threads up here. So it's just a little more convenient. And then the name of the binary. Now, if I want to do a hybrid job, that is, again, a case where I'm using both types of parallelism, so shared memory and distributed memory with MPI. So in this case, I'm only having one MPI process per node, having 2 nodes, but I'm going to have 36 threads. So I'm using shared memory across the nodes, but then I, of course, need one MPI process for the nodes to talk to each other. So when I do that, I specify this here, and then I just say omplace. I don't have to give it any of these options because omplace will take what's available in this resource statement from PBS and then specify that to the executable. So it kind of handles everything behind the scenes, which is nice. And you can have finer grained control if you want. There are options available and they're documented, but this is just a basic example. And it's important to note that this omplace command is from SGI. It's a piece of software that they provided, so it only works with the SGI MPT MPI library. So if you're using Intel MPI or Open MPI or something like that, this won't be available. And there are different ways to do this task pinning, but we don't document that explicitly since it's not the default MPI implementation on the machine. One last job example. This is a functionality that was available on Yellowstone and will similarly available on Cheyenne. It's a pretty useful idea. So let's say I have a script, could be a Python script, for example, or it could be a Fortran program or whatever, but it's a serial program, so it doesn't actually have MPI parallelism or doesn't have OpenMP threads, but I want to run that command, or I want to run different commands on different data files, and I want to do that all in the same job. So this is a form of parallelism called embarrassingly parallel. Now, what I can do that using a command file job, and this is the contents of a command file. It's basically a text file, and in it I can specify the commands. In this example, they're all different exe files, but they could all be command1.exe. It could be the same exact script. I'm specifying different inputs to it. You'll notice I'm using the redirection to specify the input, and then I'm sending the output to different files as well. Now, in a PBS job script, what I would do then is I would select a number of CPUs and a number of MPI processes that matches the number of lines in the command file. And then I would set this environment variable, MPI shepherd, to true. And what this does is this tells MPT that I have this serial program that I want to run a certain number of times, in this case 4. And I'm going to specify the details of that in this command file. And now there's an additional argument to MPI exec, this launch _cf.sh, and that script will handle all the stuff behind the scenes. So this is a nice way to exploit parallelism on the batch nodes, even if you have a serial program and you have different data sets that you want to operate on. Okay, so where can you run these things? This is the list of queues. It's very similar to what we have in Yellowstone. There's a couple small changes, but overall, you'll have the capability queue, which is a off-hours queue. There's the premium queue, which has a higher queue factor, meaning that your charge is a little higher, but it also allows you to have higher priority. There's a share queue, which is a new addition. Now, this allows for interactive use for debugging and other tasks on a single shared 128 gigabytes, so high memory node. Now, you can't request a whole node here. That's why it's called shared. This would be a node that you'd be on that would be shared among other users. But it's a good place to do these small tasks. Now, if you need a whole node or you need multiple nodes, we'll still have the small queue. That's another good place to do testing, debugging, profiling. We don't expect there to be production workflows in there. That would be a thing for a regular queue. There's also economy. If you don't need your job right away, it has a lower priority and a lower queue factor, so you get charged a little bit less, but it'll take longer for your jobs to get through the queue. Then there's a standby queue, which you shouldn't directly submit to, but you can see it in the queue listing. And that's used when you've exceeded your allocation. We still allow you to submit a job, but it goes into the standby queue which basically means it could theoretically run if there's a real lull in jobs in the machine, but it's generally just a waiting place until your allocation is back in good standing. Okay, so submitting jobs to and querying information from PBS. So we've looked at the job scripts, but of course we need to interact with PBS to submit those. On Yellowstone, it's B sub. On Cheyenne, it's Q sub. So if I want to submit a job script to PBS, I can use Q sub. Here's the script example. It would simply be Q sub job underscore script. Well, the name is irrelevant, but this is the job script that I've come up with. It's jobscript.pbs. I think it's a good idea to have PBS somewhere in the name, and that's a good way to know that this is a PBS job script and not an LSF job script, and vice versa. At least while both machines are running and you have shared file spaces, I think it's a good way to keep track of those things. You can also submit an interactive job. This is the full command, so I would do a Q sub dash capital I and then dash lowercase l. I'm sorry that those are the same looking. That's just the font, but that's a capital I and lowercase l. Here I'm requesting one node. I don't have to write the number 1 if I'm only asking for one of them. So select equals with 36 CPUs, 36 MPI processes. I'm asking for 10 minutes of wall time. I'm asking for the share queue, and I'm specifying my project here. Now, you'll notice that since I've asked for 36 MPI processes on one node and the share queue, this submission actually won't work because the share queue is only 18 or less. So this would be a good job for the small queue, which also allows for interactive jobs. Now, we've also made a kind of convenience command here. This is a script, which it's called Q interactive. You can only run it if you have the NCAR env module loaded. That'll put that into your environment. But what you can do is you can run Q interactive and then give it your project code. And then what it will do by default is give you a 1 core job for 1 hour. And that should be on the share queue. Now, you can specify other resources. If I want to get a full node or I want to get a couple nodes, I can specify that using this same syntax to this Q interactive command. Basically just saves you some typing, makes it a little more convenient to get an interactive job. There's QStat. This is how you query information about a job. If you give it a job number or job ID, that's how you would look it up. So this is the same thing as bjobs. If I do qstat-u and then my username or $user, I can get a summary of all of my active jobs. That's important. If you don't specify your username, you'll get every job on the system. It will be a big printout. That's different from the bjobs default, which if you just type bjobs by itself will give you only your jobs. So it's something to keep in mind. If I use qstat-Q and give it a queue name, I can show the status of either a specified queue, or if I leave that out, I can get all of the queues. And that's just to get an idea of resource utilization across the cluster. I can cancel a job with qdel. It will kill a job if it's running, or it will just delete it if it's queued. Now, it's important to note that while the concept of backfill windows does exist in PBS, meaning that if there's a giant job of, say, 1,000 nodes that's going to get scheduled to run in the system in 4 hours, and there's 100 nodes that are available and just kind of waiting for that in that 4-hour period, if I specify a small job that's, say, 2 hours long and 20 nodes, it could get backfilled into that open window by PBS if I submit it. So that still works, as it does in LSF. But in LSF, you can actually search for those backfill windows with certain commands. I think it's bfill is one of them. That capability is not available in PBS, so you can't actually see what windows are available. So it's, a little piece of information that unfortunately was lost, but backfilling still does happen behind the scenes. Okay, let's again go into the terminal here, and I can show you some more commands. So if I do a qstat right now, then this is just qstat by itself. See, I get a long printout of all the jobs that are currently running. Well, it's not too long, but it will be much longer when all the users are on the machine. If I do a qstat-u and then my username, you see I get nothing because I don't have anything running at the moment, but if I had some jobs running, there it would be. So I have the NCAR env module loaded, so I can run this qinteractive command, and you'll see that I get a job here. So now I'm in an interactive job, and now if I do qstat-u and then my username, you can see that I have this one core job running for 1 hour. I can get more details on that job if I want by using the -f 982874. Now this will give you a lot of detail, so you either get a tiny bit or you get a ton. But if you're trying to figure out what's going on with your job, that can be a useful command. Okay, let's exit out of that interactive job. So if I do qstat-q, then I can see all of the queues that are currently running, and you'll see that it matches, for the most part, that list that I gave earlier. You can see the number that are queued, the number that are running, and the number that are held. Okay. Now, one thing to note, you can get a brief history of jobs that you've run recently, meaning over the past couple of days, if you use -x. So if I do this right now with u and then Vanner WB, you'll see it's again, there's nothing in the list because I've exited out of that interactive job. But if I run that command with the x in there as well, so now it's -xu, you'll see all of the jobs that I've run recently. And that interactive job is at the very bottom, one core there. But you'll see I've run all of these jobs over the past couple of days. So that's a good way to get your immediate history of what you've done. Okay. So managing your compute time allocation. These are just some kind of good rules of thumb to think about. So after you compile a program, it's generally a good idea to run a small test job before your large simulation. Obviously, if you know that this configuration will work, if you've run it hundreds of times, it's probably not a step you need to worry about. But if you're running a CSM configuration or some code that you've written yourself for the very first time, it's generally a good idea to run it at small scale first. You don't want to run a giant job, have it crash halfway through, and then waste a good number of compute hours. Now, for single core jobs, again, it's a good idea to use the share queue. That avoids being charged for unused core hours. So on exclusive queues, which is most of them, like the regular queue, for example, the way you get charged is it takes your wall clock hours of the job times the number of nodes you use times 36 cores per node times the queue factor, which for the regular queue is 1, but for other queues can be different. And that's how you'll get what your charge is for that job. Whereas on the shared queue, it's the number of core seconds that you've used. So that's different from wall clock. Wall clock is I have the CPUs requested as part of the job, and whether I'm using them or not, if my job is running, those are wall clock hours. Whereas here, it's only if your program is actually using the CPU at that time. So it's the number of core seconds divided by 3600 times the Q factor. So again, this is a good way to save yourself some allocation if you're running something that is a serial program or you only need part of a node. And then the same guidance applies with Yellowstone. So it's a good idea to use the data analysis and visualization clusters for programs like NCL, Python, MATLAB, R, as well as interactive visualization programs like Vapor. For one reason, they'll be much more responsive. Like Vapor is going to be more responsive on Geyser simply because of the software library there than it would be on Yellowstone or Cheyenne. So it's generally a good idea to run those there. And for NCL and Python script, all these scripts, you'll have more memory available on a Geyser node than you generally will on a Cheyenne node. So it's another good reason to hop over there. Okay, so data storage. This again should be pretty familiar if you're working on Yellowstone. So you have these different spaces. You have your home space, which is Glade U home username. There's a quota of 25 gigabytes. If you run the quota command, it'll show 50 gigabytes, but that's because there's a duplication of your data for redundancy. It makes your data more secure. There's also backups and snapshots, so your data is very, very safe if it's in the home space. This is a great place to store settings for programs, to store code, and to store other things that you consider of the highest category of valuable. Now then there's the workspace, Glade P work, my username. The default quota is 512 gigabytes. It's a stable space, but there are no backups. So it's probably a good idea to keep things like run directories as well as input data for your models, assuming that it's not too large. Some people have access to project spaces, and that's going to vary on a case-by-case basis, as well as the size will vary. It's the same thing as with the workspace. It's stable, but there are no backups. For long-term storage, HPSS is the tape archive is a good place to store things. This you would use an interface HSI to access the space, and it will look like /home/username. Here the quota is a bit different. There's no absolute quota, but how much data you have determines what your terabyte year charge is. This again is stable, but no backups, and storage limits depend on your allocation. Now, it's important to note that data that's on the tape can't be used interactively. If you want to use data as part of your job, you have to bring it back to the disk spaces, which is the Glade file spaces. And then finally, there's the scratch space. The default quota is 10 terabytes. It's important to note that this space is at risk. It's purged at intervals. So current interval is 45 days. If you have a file that's been on scratch for 45 days, it is at risk to be purged. So this is not a good place to do long-term storage. This is a good place to write data from your model runs, and then when your model run is done, to move it somewhere safer. And some things like CESM have scripts to do this for you. So it's a good idea to move data when you're done with it on scratch. Now, if you're running on both systems, you'll have two scratch spaces for a short time, and this is just because of the way that the transition for the Glade file spaces is being done. So phase one will be in place very soon. And during this first phase, if you're running on Yellowstone, you'll actually see two scratch file spaces. You'll see Glade Scratch, which is the one you're used to, and then you'll see Glade Scratch _ Cheyenne, and this is the new higher speed Glade 2 spaces. And then you'll also see, if you're on Cheyenne, Glade Scratch, which is the same exact space as Scratch Cheyenne on Yellowstone. So that's a good way to transfer data, because ultimately this old Glade Scratch space will be retired. That will happen in phase 2, which will be a certain period of time after phase 1. And during phase 2 on Yellowstone, you'll see Scratch Old, which will be turned to read-only, so you won't be able to write more data to Scratch Old. And as a result, Scratch Old will eventually empty because of the purge, which will still be active. So after 45 days, once we set it to read-only, it should be pretty much empty. And on Cheyenne, you'll be able to see your Glade Scratch, and this, again, will be Scratch Old, and you can take care of that movement of data. So again, files will still be purged on Scratch Old, so it's a good idea to move them elsewhere. Okay, so again, some general rule of thumb tips for storage. We have this command, if you haven't used it before, it's Glade Quota, and that's available on both Yellowstone and Cheyenne. It's a good way to keep track of your allocations. It basically shows you how much space you're using relative to your quotas. It's a good idea to archive large numbers of small files, so that limits wasted space on Glade. Glade has a minimum size of a file can be. So even if the amount of data in a file is less than that size, the file will take up that much space on Glade. So as a result, if you have a ton of very small files, like 1 or 2 kilobyte files, it's a good idea to throw those into an archive, into a tarball or something. That'll make things more efficient. If data isn't needed for immediate access, move it to HPSS. So this isn't a big HPSS tutorial, but some basic commands with HSI cput. You can take a file from Glade and move it to the tape. With HSI cget, you can get a file from the tape and bring it back to Glade. So you would run these commands from Glade. Or I could just run HSI, which will put me onto a system for the tape archive, and then I can run these commands, just cput, cget, from the tape side of things and bring them back to Glade there. So large collections of files can be combined while transferring using the htar command. This is more efficient than simply using HSI to move a ton of small files to tape. Each operation takes a certain amount of time, so if you can move one file, that's going to be more efficient for you. So we have a question here. HSI should not be run as a submitted parallel job, right? So I guess it depends on what you mean by a parallel job. When you run HSI, which I assume means multiple CPUs, so HSI is a serial command. You can submit 5 concurrent file transfers with HSI, but that's going to be 5 data transfer operations which don't use 5 CPUs. So in general, yes. If you are running HSI in a batch job, you want that to be a batch job that just uses 1 CPU, because that will be the most efficient thing for you to do. And we have the HPSS queue, which is specifically set up to allow you to do this. So rather than running a HSI command or an htar command within another job script that might have many nodes allocated to it, it's a good idea to create another job that runs after the model job that's just 1 core, a serial job, and then runs those HSI commands. So let me know if that didn't address the question. Okay, great. So we have a question from the room, which is it a good idea to immediately copy stuff to HPSS? So the question is, isn't the general workflow that you would output data to Scratch or Work or something, and then kind of work with it for a little while before archiving it in tape? And that's true. I would say there's 2 general uses for tape. One of them is I've done everything I want to do with this data right now in terms of analysis, but I'm going to need it at some point in the future, so I'm archiving it for the long term. And then there's also just a matter of data redundancy. If it's a good place to have a backup. We don't generally advise you to back up every single thing onto tape necessarily. It might be a better idea to back up certain things to your workspace. Tape has certain uses that it's good for, like large model files or large observational data sets. But you certainly don't want to be archiving a lot of code, for example, there. That would probably be a better thing to have in your home directory, for example, for long-term storage. Or if you're using version control somewhere like GitHub. So yeah, I wouldn't say it's necessarily always the intention to immediately write it to tape. But if I'm, say, running an ensemble of models and I know I'm going to use up more space than is in my Scratch allocation, after each ensemble is done, I could write that to tape, and then when I'm going to do my analysis, I could pull it back to Glade. So that would be an example of that intention. Okay. And then there's an example of the htar command. So this looks very much like the Unix tar command, except it interfaces to HPSS. So here I say the name of the tarball, and then here I give it, in this case I'm giving it a directory. I could give it a list of files. And the nice thing about htar is that it combines that tarring operation as well as the transfer to tape. And if you have things in tar balls, when you move them to tape, not only does it make the transfer operation more efficient, but it also makes it a lot easier to pull files back from tape, particularly if I need all of them. I only have to do one get operation instead of hundreds, for example, if I have a lot of files in my tarball. So when you can, it's a good idea to use HTAR. Okay. So some general things to keep in mind. Yellowstone, Geyser, and Caldera, for the time being, will continue to run LSF. So again, it's a good idea to keep your job scripts organized. I like to have the .lsf or .pbs syntax. That helps me know what I'm looking at without having to open the file. So access from both file systems, from both clusters, should make data management easier, but pay attention to where you've compiled programs. Again, it's probably a good idea if you have two different builds of a model to maybe have one in a Cheyenne directory and one in a Yellowstone directory, and that way you can keep things organized and not have to do some investigation if it's months later and you can't remember where you built that version of WARF. And if you want to configure settings in your startup files for both machines, you should make sure that if you want to run a command only on one system, you should make sure that that actually happens. And here is a pretty simple example of how to do that. So when I say startup files, and specifically I'm talking about the .tcshrc file if you're running C shell, or the .profile file if you're running bash. Here are examples of both. Now in the C shell file, basically what I'm saying here is, am I running an interactive session, SSH session? If I am, set up an alias, set up a prompt. These things are relevant to both machines, so I want to set them regardless of whether I've logged into Yellowstone or Cheyenne. But here I have a little conditional statement which says if the host is a Yellowstone login node, I'm creating an alias for LSF where I'm emulating the QStat behavior in PBS. And then in Cheyenne, I'm doing the opposite where I'm emulating the bjobs behavior in PBS. So it's just whether I see everybody's job or whether I just see my jobs. This is a pretty trivial example, but you can get more complicated in terms of specific settings for each machine. And then here's the bash equivalent. Again, I have my commands that I care about for both machines, and then I have ones that are specific to Yellowstone and specific to Cheyenne. And in this case, I'm also moving some commands that are specific to each in separate files that I can then source. So that's another way you can do it for organization. Okay, so that's pretty much all I wanted to talk about today. Just some final information here as to where you can get more help. There's our website here, which I can bring up in another tab. Let's see, if I just Google CISL help, and then I can get the page here which lists the consultant on duty. It lists our hours, and then you can send a help ticket here. Also on the left side here, you have all of our web documentation, and BJ's put that in the ReadyTalk link, this specific Cheyenne information, which you can see down here. So this has basically a lot of what I've talked about today, but in more detail. For example, if I want to look at how to run jobs, I can click there and get a lot more information about all the various subjects. Just as one example, if I go to the running jobs page, I can see the queues as well as some of the commands. There are things I didn't talk about today as well, things like how to use hyperthreading on Cheyenne. So it's a good idea to look at these pages if you have any questions or just want a refresher as to what goes on in our systems. So also, if you want to talk to us directly, here's our walk-in location here at the Mesa Lab. The email is CISL help, and that'll be for any computing support ticket. And there's the phone number to get to the help desk. Finally, if you have specific questions from today's talk, or you want to give me some feedback, here is my email. And also just, for science questions, things like how to set up your configuration for CESM or WRF or something like that, that's something that you would consult their relevant support resources. So maybe you would send an email to WRF help, for example, for WRF, or go on the CESM user forum. If you have technical questions, that's certainly something to send to the help desk, but they're going to have more of that in-depth scientific understanding of the models and be able to help you set up your specific configuration. So that's about it. I'll stick around for a couple minutes in case any questions pop up in the chat, but otherwise, thanks for signing into the Ready Talk today, and hope to get you on Cheyenne pretty soon. Thanks.